Friends, welcome to the tutorial series on network analysis made simple. During our earlier tutorials titled Introduction to Laplace Transforms, we learned the basics of Laplace Transforms. During the next two tutorials titled Laplace Transforms of Special Signal Waveforms, we learned step function and ramp functions. During this tutorial, we shall revise only unit step and unit ramp signals in brief. Later, we shall study unit rectangular and unit triangular signals in detail. Friends, the unit functions are very much useful in the study of signal representation and signal processing. We also discuss regarding the modified ramp signal which forms the basis in the study of impulse functions during our subsequent tutorials. Hope the discussion will be lively and interesting. Friends, first let us consider a unit step function shown in figure. You know that f of t is equal to 0 for t less than 0 and is equal to 1 for t greater than or equal to 0. The function shown occurs at t is equal to 0 and is represented as u of t. You also know that L of f of t is equal to integration 0 to infinity f of t into e to the power of minus st dt. By substituting the value of f of t and integrating, we get L of f of t is equal to 1 upon s. Next, consider a delayed unit step function delayed by a seconds as shown in figure. Its mathematical model is f of t is equal to 0 for t less than a seconds and is equal to 1 for t greater than or equal to a seconds. The function occurs at t is equal to a seconds and is represented as u of t minus a, that you know. By using the time shifting theorem, we know that L of f of t minus a is equal to e to the power of minus as into f of s, and hence we get L of f of t minus a is equal to e to the power of minus as into 1 divided by s. Friends, next we shall consider unit ramp signal which occurs at t is equal to 0 as shown in figure. The function has slope of 1 unit and hence its mathematical model is f of t is equal to 0 for t less than 0 and is equal to t for t greater than or equal to 0. The function is represented as r of t. So, L of f of t is equal to L of r of t is equal to integration 0 to infinity t into e to the power of minus st dt. By using the rule of integration by parts, by integrating t into e to the power of minus st within limits 0 to infinity, we get L of r of t is equal to 1 divided by s square. Friends, if you need more detailed explanation regarding solving this integration, I suggest you go through my earlier tutorial video titled Laplace Transforms of Special Signal Waveforms Ramp Function. Friends, next we shall take up a unit delayed ramp function delayed by a seconds as shown in figure. The function has a slope of 1 unit and is represented as f of t is equal to r of t minus a. Its mathematical model is f of t is equal to 0 for t less than a seconds and is equal to t for t greater than or equal to a seconds. By using the time shifting theorem, we get L of f of t minus a is equal to L of r of t minus a is equal to e to the power of minus as into f of s, and hence L of r of t minus a is equal to e to the power of minus as into 1 divided by s square. Hope you have understood it. Friends, rectangular function has extensive applications in signals and systems. Here we are interested in a unit rectangular function. For your information, rectangular function also is known as gate function, pulse function or window function. This function is true between specified period of time and is zero outside the window. A unit rectangular function is one whose area enclosed along the time axis is unity. That is, area A is equal to 1 unit. I will clarify this aspect as we proceed further. Symbolically, the function is represented as rect of t or pi of t. Few examples of rectangular functions, their representation and their mathematical models are explained during the next discussion. Consider the unit rectangular function shown in figure. You can observe that the function is true between time t is equal to minus 0.5 and plus 0.5 seconds. If you observe the function, you find that it has a base of 1 unit and height of 1 unit. Hence, area is equal to 1 into 1, which will give us 1 unit. So, it is called as unit rectangular function. Its mathematical model can be written as rect of t is equal to 0 for t less than or equal to minus 0.5 seconds and 1 for time t between minus 0.5 to plus 0.5 seconds, and again it is equal to 0 for t greater than or equal to 0.5 seconds. Friends, I prefer to call this function as a unit rectangular function which occurs at t is equal to minus 0.5 seconds. Consider another unit rectangular function shown in figure. The function is true between time t is equal to minus a by 2 and plus a by 2 seconds as shown. It has a pulse height of 1 by a units. It has a base of a units of time. Therefore, area enclosed along the time axis a is equal to a into 1 by a, which will give us 1 unit. So, this function also is a unit rectangular function. Its mathematical model can be written as rect of t is equal to 0 for t less than or equal to minus a by 2 seconds and is equal to 1 by a for t between minus a by 2 to a by 2 seconds and again is equal to 0 for t greater than or equal to a by 2 seconds. This function also is a unit rectangular function which occurs at t is equal to minus a by 2 seconds. Friends, consider another unit rectangular function shown in figure. The function is true between t is equal to 0 to a seconds. The function has a base of a units and a pulse height of 1 by a units. Hence, area a is equal to a into 1 by a, which will give us 1 unit. Its mathematical model can be written as rect of t is equal to 0 for t less than 0 seconds and is equal to 1 by a for t between 0 to a seconds and again is equal to 0 for t greater than or equal to a seconds. This function, I prefer to call it as a unit rectangular function which occurs at t is equal to 0. Why? Because this being the gate function or window function, it may occur at any time t. Friends, to emphasize the concept of unit rectangular function, let us solve one example to show that the function is unit rectangular function for the function shown in figure. We are also required to find the Laplace transform of the given function. As I expressed earlier, to check the validity of the unit property, we have to find the area enclosed by it along the time axis. Observe the given function. It has a pulse width of 4 seconds and a pulse height of 1 by 4 units. So, area A is equal to 4 into 1 by 4, which will give us 1 unit. Hence, the function is a unit rectangular function. To find its Laplace transform, we see that number 1, there is a shifted step of 1 by 4 units at t is equal to 2 seconds. Let it be f1 of t and f1 of t is equal to 1 by 4 u of t minus 2. Number 2, next, there is a shifted negative step of the same strength of 1 by 4 units at t is equal to 6 seconds. Let it be f2 of t and f2 of t is equal to minus 1 by 4 u of t minus 6. So, f of t or rect of t is equal to f1 of t plus f2 of t. By substituting the values for f1 of t and f2 of t, we get rect of t is equal to 1 by 4 u of t minus 2 minus 1 by 4 u of t minus 6. By taking the Laplace transforms, we get L of rect of t is equal to f of s is equal to 1 by 4 into e to the power of minus 2s by s minus 1 by 4 into e to the power of minus 6s by s. Friends, next we shall consider another important function called unit triangular function. The triangular function also is known as hat function or tent function. Maybe as it looks like hat and tent, these names would have been used in practice. Similar to unit rectangular function, unit triangular function also will have unit area enclosed along the time axis. Observe the unit triangular function shown in figure. It is represented as tri of t. Observe that the function is 0 for t less than minus 1 second. Also, it is 0 for time t greater than or equal to 1 second. Between time t is equal to minus 1 second and plus 1 second, the plot of the function takes the form of a triangle. Observe that the base of the triangle has 2 units of time and its height is 1 unit. We know that area of the triangle is half into base into height. Hence, area A is equal to half into 2 into 1, which will give us 1 unit. Hence, the function is a unit triangular function. Its mathematical model can be written as tri of t is equal to t plus 1 for t between minus 1 and 0 and minus t plus 1 for t between 0 and plus 1. Consider tri of t is equal to t plus 1 for t between minus 1 to 0. If you observe the function between minus 1 second to 0, it is a straight line touching time axis at t is equal to minus 1 second having y-intercept of 1 unit. So, if we substitute t is equal to minus 1, we get 0. If we substitute t is equal to 0, we get the rect of t is equal to 1. Similarly, if you consider tri of t is equal to minus t plus 1 for t between 0 and 1 second, if we substitute t is equal to 0, tri of t is equal to 1. And if we substitute t is equal to 1, then tri of t is equal to 0. Hope you are convinced. To clarify the concept, consider another unit triangular function shown in figure. The function is 0 for t less than 0 and also it is 0 for t greater than or equal to 2 seconds. Between the time t is equal to 0 to 2 seconds, the function plot is a triangle. If we find the area enclosed along the time axis, we get area A is equal to half the base into height. Base is 2 seconds and height is 1 unit. So, area A is equal to half into 2 into 1, which will give us 1 unit. Hence, the function is a unit triangular function. Its mathematical model is tri of t is equal to t for t between 0 and 1 and tri of t is equal to 2 minus t for t between 1 and 2 seconds. Friends, consider try of t is equal to t for 0 and 1 second. If we substitute t is equal to 0, we get try of t is equal to 0. If we substitute t is equal to 1, we get try of t is equal to 1. That is simple. Similarly, consider try of t is equal to 2 minus t for t between 1 and 2 seconds. If we substitute t is equal to 1, then try of t is equal to 2 minus 1, that is equal to 1. If we substitute t is equal to 2, then try of t is equal to 2 minus 2, that is equal to 0. So, friends, I hope you are convinced. I think now you are ready to solve the numerical problem on unit triangular function. We shall proceed further. Friends, now we shall solve a numerical example to show that the given function is a unit triangular function plus we shall find the Laplace transform of the function shown in figure. Observe the function. The function takes the plot of a triangle between time t is equal to 0 to t is equal to 4 seconds. Area enclosed along the time axis is area A is equal to half the base into height. Base is equal to 4 seconds and height is equal to 1 by 2 units. Hence, area A is equal to half into 4 into half, which will give us 1 unit. So, the given function is a unit triangular function. To find the Laplace transform of the function, observe that there is a ramp of half divided by 2, which is equal to 0.25 unit strength at t is equal to 0. Let it be f1 of t and f1 of t is equal to 0.25 r of t. To obtain the given function, we have to add a negative ramp of twice the slope, that is 0.25 into 2, which is equal to 0.5 units at t is equal to 2 seconds. Note that. Let this function be f2 of t and f2 of t is equal to minus 0.5 r of t minus 2. If we add this function f2 of t, the function traces down below crossing time axis at t is equal to 4 seconds. Note that. So, to bring the trace along the time axis, we have to add a positive ramp of slope 0.25 units at t is equal to 4 seconds. Let this function be f3 of t and f3 of t is equal to 0.25 r of t minus 4. By adding all the three functions, we get try of t is equal to 0.25 r of t minus 0.5 r of t minus 2 plus 0.25 r of t minus 4. By taking the Laplace transforms, we get f of s is equal to 0.25 by s square minus 0.5 into e to the power of minus 2s by s square plus 0.25 e to the power of minus 4s by s square. Hope you understood it. Friends, next we shall study regarding an interesting function which is called as a modified ramp. It is interesting to note that the differentiation of a modified ramp results in a unit rectangular function. Friends, modified ramp is a concept. Observe the function shown in figure. The function is 0 for t less than t1. It is a ramp between time t1 to t2. The strength or the slope of this ramp is 1 by a units. After time t2, the ramp turns out to be a unit step which occurs at t is equal to t2 seconds. Note that. So, the ramp between time t1 and t2 can be represented as f of t is equal to 1 by at for time t between t1 to t2. If we find the differentiation of this f of t, we get d by dt of f of t is equal to 1 by a, which is a constant. Then, what does this mean? Because the function is 0 for time t less than t1, the differentiation of the function f of t for this range of time is 0. Between time t1 to t2, the differentiation of the function 1 by a into t is 1 by a units, which is constant. And after t2 seconds, again the differentiation of f of t is 0 because f of t is constant equal to 1 unit after t2 seconds. You may note that. So, d by dt of f of t of the entire function results in a rectangular function as shown in figure. If you find the area of this rectangular function enclosed along the time axis, we get area A is equal to base into height. Base is A units and height is 1 by A units. So, area A is equal to 1 by A into A, which will give us 1 unit. Hence, the differentiated modified ramp function results in unit rectangular function. As I told you, a modified ramp is a concept. This concept we shall use while we study impulse function in the subsequent tutorials later. Friends, during this tutorial, we understood the representation of different unit functions such as unit step, unit ramp, unit rectangular and unit triangular functions. We also understood the concept of a modified ramp and saw that the differentiation of a modified ramp results in a unit rectangular function. This modified ramp concept will be helpful in understanding another important function called impulse function. Hope you will join me during the next tutorial of impulse function also. Friends, if this tutorial has kindled some of your thoughts, please forward your feedback and suggestions to my email. Thank you for watching this video.